今ピント合わせてます。
I think it's around the Orion. I'm focusing right now. Now we're beginning to see more clearly. I'm sorry to kept you waiting. So you can see the horizontal line, can you? And below that, there are stars. Can you see them? Furukawa-san, what is the direction that you're trying to film?
はい。右舷側ですのでニュージーランドの方です。
Yes, we are facing towards New Zealand. There are stars, and I think you can see some light, but maybe you cannot see the night view yet.
北の方向向けてます。
We can, and the camera is facing north. And around the Orion, we see something like film.
はい。はい、こちらこの地球の表面のところにうっすらと光が見えると思うんですけども、これは
I think you can see some dim light on the surface of the Earth, and this is not reflecting the sunlight. It's called the air glow. The atmosphere of the Earth is glowing itself. Oh, it's glowing itself? Yes. I didn't understand what he was saying.
Back again. This time I'm scrutinising the Japanese space agency. Already I see some problems. They claim to be here facing north and at the same time facing New Zealand. I don't know about that. But you can see that little atmosphere that they're talking about. Yeah, if you notice, doesn't quite look right, but it might just be the dome. You don't know, could be anything. Well, anyway, up here they start talking about the aurora, so we'll get onto that.
Is that the aurora? Yes. Electrons are falling, and these are oxygen atoms that are emitting light. They are probably at an altitude of about 100 kilometers from the Earth's surface. And you can see some stripes or striations. There are various energy levels associated with different electrons. So some with higher levels can actually fall to lower altitudes, whereas those with low electron energy levels stop at higher altitudes. This is live, right? Yes, it is. But this is looking from very far away. Yes, but if you're looking from the ground, you can only just see it in a line, probably. You can see it's actually kind of forming a circle or a half circle. So it means we are actually looking at half of this, probably across 5,000 kilometers or so.
はい、オーロラのリングの端側の地球の縁の
We can see the edge of the ring actually disappearing to the other side of the rim of the Earth. This is live, right? Yes, this is live from the International Space Station, and it's a real aurora. Our wishes are coming true. Great. Takeda-san, would you like to ask any questions? Are all astronauts used to seeing auroras like this? My name is Soun Takeda, by the way. Well, it depends. Sometimes you get to see them, sometimes you can't. So today I think we are extremely lucky that we are able to see this during this limited time frame. This is Yuki Nakama. I'm sure you've seen a number of auroras. What about today's? How do you rate this?
とてもくっきりと綺麗に見えてる。
This one is very clear and beautiful. Sometimes it's paler, sometimes it extends to a higher altitude, sometimes it's thicker. There are various forms that you can see on different occasions.
Well, first off, I changed the exposure and stuff just because it didn't look right. And if you notice, stars are moving differently compared to the aurora, which is wrong. You see it's bobbing in and out of the aurora. That's way out. And then you see that it gets covered with something. The aurora gets covered, and then you see down in the little bend there, you see that it's like a right angle. See that? So to me, that tells me they're covering it with something. And the way I think they're achieving it is it's being projected from the inside. There's a window between them and the stars. They're filming the stars out the window. The aurora is just a reflection on the glass, and he's holding the camera with his left hand and holding something out with his right hand and bobbing it up and down in front of the aurora. So he's getting it in between the reflection in the glass and the source of the light of the aurora. And you'll notice that the timing of whatever he's putting in front of it, the way it moves up and down, you'll notice when it stops and then rises and stops and rises, you'll notice that it moves with the camera. The camera bobs up and down sort of in time with it. And that to me tells me also that it's him holding the camera with his left arm and holding something out with his right arm, and he's lifting it and dropping it. So here he's starting to move. That's why the camera moves around, because he's moving out to put something out there. Then he puts it up and down, and you'll notice that it moves with the camera. When it stops, the camera sort of stops, and then lifts, and the camera lifts. See? So that, to me, it's just the balancing from him lifting up and down with his right arm, and the camera moving a little bit, and it's moving sort of the opposite direction to what he's lifting his other arm. Sort of just from doing that, it's, yeah. And so the camera moves a little bit, but it's noticeable, and you can actually notice that it's in the same time with whatever he's doing. So watching this made me start to think also about the auroras, and that also made me think, because I have a very good capability of picking contradictions. And this helps in this field, because thinking about the auroras got me back onto thinking about the damn speed that they say that the globe is going. And just because I find clashing information, I found someone to explain the speed again and the movement and stuff, just to refresh us on it. And then I'm gonna pull it apart like I normally do, because yeah, it doesn't work. It clashes, doesn't fit together probably. But yeah, so that's coming up. But first, yeah, if you just notice the movement, and it's a bit easier to notice here in the original footage that he's putting something out. You can actually see the edges of it. It's a very poor effort, don't you think? I do. Well, anyway, moving on to the speed of the globe Earth, and then I'll talk about why it doesn't fit with what we're told. Okay, mysteries from the globe, take it away.
The other day I did this video about time dilation, or the idea that time is relative to your current speed. You know, the faster you go, the slower time goes. But that got me thinking, there is no such thing as not moving. Hey everybody, thanks for watching D-News. I'm Trace. You might think that you're just sitting there watching this video. Maybe you're in a car, you're on a train, or in an airplane. Even if you were at home on your couch though, trying to be as still as possible, you are still traveling a lot of miles per second every second. Sit still and think about that, just for a second. You just traveled a really far distance in space. The question is, how fast are we moving? And it's far more difficult to answer than I thought, because there are so many moving parts. Literally, no pun intended. Okay, pun kind of intended. So let's go through each level of motion and then add it all up at the end. Starting small, you're not moving. Just to keep it simple, let's say you're standing on the equator. As the Earth rotates, the equator is going the fastest, and the poles are going the slowest. If you were standing on the North Pole, you'd simply rotate once in a circle every day. But on the equator, you're going about 1,000 miles an hour in a circle every day. You don't feel it for the same reason you aren't stuck in your seat while a plane is flying. Speed is relative. You only feel it when it changes. So anyway, you're already going 1,000 miles an hour as a person by yourself. The Earth is traveling around the sun once per year. It's a trip of 584 million miles. To get the sun back to the exact same point in the sky every year, it has to go all the way around. That means the whole planet is flying at 66,667 miles an hour as a planet on top of your 1,000 miles an hour. You get where we're going? Then zooming out further, we are all tied to the movement of the sun. The sun is flying through our galaxy with all of its planets tucked into its gravity. Scientists determined the sun is moving toward other stars at around 45,000 miles per hour. We're also moving up relative to the galactic disk at about 15,700 miles an hour. We're not going to fly out of the galaxy, by the way. The gravity of all those other stars is going to slow us and then pull us back down in the next 14 million years. We'll get to that later. And since we're about halfway out of the center of the Milky Way, and as far as we can tell, the galaxy rotates once every 2 to 250 million years, we're moving approximately 550,000 miles per hour as a solar system. You'd think that might be far enough, but we are not done yet, because you, the planet, the solar system are all moving, and so is the whole galaxy. Our galaxy is headed toward the Andromeda galaxy at a pretty good clip. Numbers vary, but a recent 2013 Space.com piece clocked us at about 252,000 miles per hour. Again, with the three-dimensional thinking, the Milky Way is also moving toward the constellation Hydra at about 1.3 million miles per hour, and toward Virgo at about half that. So overall, the Milky Way might be traveling as fast as 2.237 million miles an hour. Another sidebar, by the way, the further away from you that you get, the more difficult it gets to measure your actual speed, because you're just moving a little bit, but the galaxy is moving 2.2 million miles an hour. The reason we use constellations and other galaxies to measure this is the same reason we use trees and mountains here on Earth to gauge distance. They are large and far enough away that they become a point of reference. We can measure our speed relative to theirs, but of course all of those stars and galaxies are also moving. And Andromeda, the galaxy, is moving, and the stars of the constellation Hydra, which is one of the constellations we measure against, is moving. Everything is moving. And the whole universe might actually be moving too. Yeah, the whole damn thing. I can get into that if you want. Let me know with a like, and if we get to 10,000, we'll come back. We'll cover that too. It's big, y'all. Okay, now to the maths. Your 1,000 miles an hour, plus Earth's 66,000 miles an hour, plus our system's 550,000 miles an hour, plus the galaxy's 2.237 million miles an hour equals about 2.855 million miles per hour, or about 800 miles every second. That's mind-boggling and kind of incredible. The reason you're not clinging to the ground with fright right now is because, again, speed is relative. You are not feeling it because we're all on this supersonic journey jet together. Us and all the stars in the galaxy. How does that make you feel? Small? Tiny? Insignificant?
Yeah, that's how you're supposed to feel. Small, tiny, and insignificant. Okay, so for starters, let's look at this. Not the speed, the spin, not the speed of going around the sun, but just the speed of, what do you say, the galaxy and the solar system. And we add that together and we get 2,787,000 miles an hour. Okay. Well, apparently, here we are. This is light traveling from the sun. And it's traveling out to all the way out to Neptune. Every second is a minute. Every minute is an hour. And if we're moving at 2,787,000 thousand miles per hour upwards. How is light going to travel? Because see, that's an hour just past there, and we've travelled 2,787,000 miles. Well, that light is travelling outwards, isn't it? It's travelling outwards, just past Saturn. So it just passed there. It's travelling outwards. So just for the light to get to Saturn, bounce off it and come back, and then for us to see it, how? We're moving away from that light. How's the light going to reflect back to us? And how are we going to see it? Yeah? And then solar flares. Solar flares can take a day or so to get to us. 13 hours and longer or something like that. I think 13 hours or something is the shortest amount of time. But even still, 13 hours? You know how far we've travelled? Away from the same spot that we were when the ejection happened. It's got to travel 93 million miles. It takes like 13 hours or something. It doesn't happen very quickly. It takes hours, longer than this takes, for the light to reach Neptune and get back to us. It takes longer than that for a solar flare to reach the Earth from the Sun. How? If we're travelling upwards, apparently, flying through space at 2,787,000 miles an hour upwards. How can a solar flare reach us? And how can light reach Neptune and back for us to see it? That's impossible. It's just another lie from the globe. See what I mean when I tell you that their own stuff clashes with itself? It's a load of crap. Look, 3 hours have passed. It's 5 hours now. 4 hours, sorry. So 5 hours. 4 hours have passed. And the light's just about to reach there. Here comes Neptune. Boom! There you go. So, how? And it's got to reach all the rest. The cop about Neptune and all that. Let's run that in reverse. Just why not? Okay. And the light's got to get all the way back, right? And it's going to take 8 hours of travel. Nearly 8 hours of travel. Nearly 8 hours of travel for it to get to Neptune and back. How can they see it with a telescope? How can they look at it? How can the light even reflect off it and get back to us? It can't. It's impossible. We shouldn't be able to see anything out there, really. Just for the simple fact that we travel away from the light's trajectory. And how are we supposed to see the sun? Like, if the light is travelling towards us from the sun, yet we're moving up, away from the spot the light was travelling towards, and we're moving up, so we're heading towards the light that was projected upwards from the sun on more of a, 45-degree angle maybe, or maybe a lot shallower, as it's probably moving a lot faster than we are. But still, that light that we hit we would be that light would be hitting us. We'd be hitting it, and it would be coming on an upward angle at us, because we're not parallel anymore. We're rising, apparently. So, therefore, the light that actually hits the Earth would be light that went up on an upward angle, not a parallel angle, not a horizontal angle towards the Earth, but one that was going above the Earth, and we rose up into that light. So therefore, wouldn't we see the sun like on a downward angle or something? It wouldn't. It would. The light that we see coming from the sun would be delayed light, and we'd be seeing it at a different point. Therefore, we would see the sun lower. It would look like the sun was lower, but the sun would actually be higher. Just the light that we received is light that was on a different angle. It wasn't coming sideways at us, so we shouldn't have seen it. We should have, that makes sense. That makes sense to me. It shouldn't hit us on that angle, it should hit us on that angle, yeah. Okay, so make your own minds up, but I'll keep fishing and keep looking and keep finding. That is inevitable. There's so much out there. There's full of lies, and yeah, I'm fishing. Find them. Okay, everybody. God bless, and have a great evening. Bye.